Does that look different? Looks very big. Like they did something with the projector. Well, so at some point, I would like everyone to come up here and choose 5 problems to do from the practice test. Whatever 5 look the most interesting to you that you're like, oh, I'd like to review those. That'll be our starting point. And otherwise, we're going to finish the problems from 3.7. So let's go ahead and do that. Let's look at the calendar here. We just had Thanksgiving last Thursday. Now here we are Tuesday. We're reviewing for your 4th test, which happens to be on Chapter 3, which we'll take on Thursday. So 2 days from now, you're going to take a test in Chapter 3. And then the next week, we come back, and it's a whole week of review. This is pretty exciting. That's nice that we can do that. We can spend 1 whole day reviewing derivatives, and then 1 whole day reviewing integrals. I will give you a practice test for that, probably on Thursday when you come in to take your test. That way, that's what we'll be doing is reviewing that practice test. And then the next week on the 12th, we'll do the final exam. Now, just so you know, in every course, you do a course survey, right? You do a course survey. Do you normally do it on paper, or do you do it online? You've probably done it both ways. Well, in this class, we're going to do it online. So as of December 7th, I'm going to put a course survey online on the Canvas homepage. So you'll just go to the Canvas homepage. It'll be there waiting for you, and you'll take your course survey. I would appreciate everybody doing it. And to make sure that everybody gets a chance to do it, if on the day of the final exam you come in and you haven't done it yet, I'll just let you go ahead and do it on the computer real quick, and then you can take your final exam. So that way I can ensure that everybody has done a course survey. It's valuable feedback to hear how you guys felt about the course and what I could do to improve it for future students. Okay, so that's what's coming up. I do have a joke for you. Why did the cowboy get a wiener dog? I don't know. Why did the cowboy get a wiener dog? He wanted to get along, little doggy. Get along, little doggy? No? All right, well, then here we go. The last problem that we were looking at was number 9. And this is very interesting, this accumulated present value. So a company is considering expanding their production capabilities with a new machine that costs, oh boy, $39,000? Did it? Yeah. So we have this machine, and the machine costs $39,000. Right? And it has a projected lifespan of 8 years. So that's it. After 8 years, the machine is going to be broken, and you won't be able to use it anymore. You won't be able to maintain it, update it, upgrade it, nothing. The machine is just trash. So if it costs you $39,000 and it's going to last 8 years, how much do you need to make from it every year just to recoup your cost? What would that be approximately? You know, you're buying a machine, and the machine is going to help you make products that you're going to sell for a profit. How much money do you hope to make off of the machine? That is, how much money had you better make from the machine? Otherwise, it's just a loss, and why would you buy the machine in the first place? So how much do you need to make from that machine every single year? Yeah, 39, 1, 2, 3 divided by 8. We better be making at least $4,875 a year. We hope. Otherwise, the machine is pointless, and don't bother doing it. That wouldn't be a good investment. Now, they estimate the increased production will provide a constant $5,000 per year of additional income. Well, that's great. So the income will be a constant flow. Income is continuous, $5,000 per year. So already based on that, you might be saying, okay, well, great, that's a good deal. Go ahead and buy it. You know, if the cost is $48.75 per year, and I'm going to make $5,000 per year, how much profit, or how much profit did we just make? What would that be? $125 per year. Now you might say, for $125 per year, why bother? Right? I mean, we could all just go stand outside and ask somebody for $125, and that would probably be less of a hassle than buying a machine and making all sorts of products. In any case, the key thing is you just want to know that you're not losing money, right? So at face value, if we went ahead and did this purchase, at least we're not losing money. So you think to yourself, well, might as well. You know, why not go ahead and get this machine? Who knows what other opportunities might come along with it? Now, on the other hand, let's see here. Money can earn 1.6% per year compounded continuously. So let's say you scrap the whole idea and you just take the $39,000 and you just invest it. Right? Or this is your what is it called? It's an alternative. In economics, what do you call an alternative? Opportunity cost, yeah, or a trade-off. So the opportunity cost is you can just take your $39,000 and invest it at 1.6% per year. Now that might sound even better because by the end of those 8 years, now you've got all that interest that you just made on your money. So now that might seem a little more tempting, especially because we're so close in that regard. So now they're asking us, should we buy the machine? Should we buy the machine or should we just invest our money? Well, the last consideration we need to take into account is this idea called present value. And what they're actually asking us is, yes, the present value of the machine is greater than the cost, or no, the present value of the machine is less than the cost. So what is present value? Have you guys already talked about that in your courses? Present value? We kind of already understand the idea of future value, like present value versus future value. When you do an investment, you've got, your traditional compounded interest formula, that the present value of your money is how much you currently have, and let's say that you invested that money, it would grow according to compound interest and give you a future value of how much money you'll have in the future. So we have to consider that the example that I've read is that, would you rather have $1 now or $1 a year from now? Which would be better, to have $1 now or $1 a year from now? Anyone? Probably, yeah, you definitely want to have $1 now, because what could you do with that $1? You could invest it, and a year from now, how much would you have? Like maybe $1.30, right? So definitely it's better to have $1 now than $1 a year from now. And in fact, if you run it backwards, okay, this $1 now is going to become maybe $1.30 in the future, and $1 a year from now would actually be how much today? How much would you have to have today such that you'd have $1 a year from now? Yeah, maybe only 70 cents. I mean, I'm not doing the math on this. But the key thing is that whatever amount you're going to get later on, that's actually the present value of that dollar later on is actually much less, because you have to figure that you could have taken that money and invested it and grown it. So that's what we have to consider about this $39,000, whether we should hold on to it and invest it and just take the earned interest, or versus this continuous income stream of $5,000 per year. Once we get all those $5,000 per year later on, how much is that actually worth now? So like, for instance, if we get $5,000 per year for 8 years, how much is that? $5,000 per year for 8 years, that's $40,000, right? So by the end of all those 8 years, that's $40,000. But how much would that be worth today? Kind of like that $1 a year from now is only worth 70 cents today. How much is that 40,000 worth today? Considerably less. And the question is, how much less? Because if the present value of that 40,000 is less than 38,000, less than 39,000, if it's only worth 38,000, should we buy a machine that costs 39,000? No, that'd be a bad deal. But if the value of that 40,000 is actually worth, say, 39,500 today, then yeah, we might as well spend 39,000 to buy something that's worth 39,500, because we immediately make some money out of the deal. Okay, so those are all the different considerations that we're talking about in this problem. Is what is the present value of the total future earning potential of this machine? How much is it worth right now today? And if that value, if the present value is less than 39,000, we probably don't want to buy the machine. But if the present value is more than 39,000, then fantastic. Let's buy the machine and we'll make some instant profit. All right, well, folks, let's do it. How do we calculate present value? I believe, oh, nope, that's not the formula. There, nope, that's not the formula. Where did I put the formula? Aha, there it is. Everyone go ahead and write this down. Continuous income stream. Suppose money can earn an interest at an annual interest rate of R compounded continuously. Let f of t be a continuous income function. So you're making continuous income. Remember, that means you're not just getting the income at the end of the year. It's like someone slowly pouring money into your bank account over the whole year. That's continuous income. The present value of the income stream is given by that. So let's start there. The present value of that future income stream goes from 0 to t, where that's how many years you're getting that income stream. F of t is the function that tells you how much money you're getting every year continuously. And then e to the negative rt, where the interest rate is the interest rate of the money you could be earning from a bank account that's giving you continuous interest. So again, what we're calculating is we have from this word problem, right? We have let's look at f of t. We have a income stream, a continuous income stream of the value of 5,000 per year. So our continuous income stream is 5,000 per year, and we're going to get that for the next 8 years. So I'm going to label that continuous income for 8 years. And what we want to do is look out into the future of how much will we have from that continuous income 8 years from now, and bring that back to the present and see what the present value is. And this is the formula to do it. So we'll go ahead and say the present value of this machine from 0 to 8 years is our $5,000 income stream. And then e to the, what was our interest rate?
Negative 0.016.
Yeah, negative 0.016 t dt. So I hope I set that up adequately about what we're really looking at. Because we're getting $5,000 per year. We're getting $5,000 every single year. So 5,000 times 8, that's $40,000. So at the end, you know, the total amount of income that came into us was $40,000. But that's $40,000 8 years from now. We have to bring that back to the present value and think about how much money would I have to have now that would result in having $40,000 in the future. So we go ahead and just do the integral, and that's it. This is the integral to calculate what that present value of the $40,000 is. The present value of the $40,000 is going to be less than $40,000. So how do we take the integral? What do we do first? Yeah, might as well bring the 5,000 out front. And then we have e to the negative 0.016 t dt. And
divide the 5,000.
do what? How do we do the integral of e to the? If you have e to the nt and you want to take the integral, what is it again? Then 1 over n e to the nt. It looks very similar to the power rule, but it's not. The power rule of x to the n, you increase the exponent by 1 and divide by that resulting exponent. So it's very subtle here, the difference between the integral of the anti-power rule, which is that you add 1 to the power and divide by the resulting power. The antiderivative of e to the nt, you simply divide by the power. You divide by the exponent that's on the e. So we'll go ahead and do that. We have here 5,000. And then we'll go ahead and do the integral. So that's 1 over negative 0.016 e to the negative 0.016 t, evaluated from 0 to 8. It's definitely a fair question on the test. I'm sure I will put it on the test. Something like
We
this.
use the equal sign and not down.
Yeah, sorry, dropped my equal sign. So now what? Now I would suggest we all have our calculator handy, and we do 5,000 divided by negative 0.016. So that gives me negative 312,500 e to the negative 0.016 t from 0 to 8. I do a lot of this on my calculator. Like when I did the practice test, I really heavily used my calculator. I still showed a lot of work because I wanted you all to see my work. But at this point, I would go ahead and just type in negative 312,500 e to the negative 0.016 times 8, and I'm going to write that value down. So that's negative 274,954,081 minus, because taking an integral is always subtracting, the lower value. The lower value is easy. E to the power of 0 is just 1, so I'm subtracting negative 312,500. So we have a double negative?
Wait.
Yeah. Go ahead, Julie.
is it the 3.2508 and negative 0.16 times 8?
Well, you plug 8 into the t value.
Yeah, that's
Yeah.
to get the.
I get negative 274,954. Yeah. All right, and then a double negative. And now, see, keep doing all this in my calculator. Now I simply add 312,500, and that gives me the final value of 37,545. Did I give you a copy of 3.7? Yeah. Okay, and that's it right there? Oh, and it has the answer down there at the bottom. Yeah. Okay, so apparently the present value of the income stream that we would get from this is only 37,545. That's the present value. And what are we thinking about doing? Spending 39,000 to buy that. That makes no sense. 39,000 is more than the present value. So if we go ahead and subtract 39,000 from that, we see that it is short by $1,454.18. Meaning we would be overpaying $1,454 to buy a machine that costs $39,000, whose income stream is only worth $37,000 in the current. Did you notice that the end of this problem is surprising? Because during our initial analysis, didn't we suggest that this was an okay deal? That if it's $39,000 currently, but in the future we're going to make $40,000 from it, that seemed like if we pay $39,000 today and we earn $40,000 after 8 years, that seemed to be a $1,000 profit. But there really wasn't a $1,000 profit. Why not? Why didn't we really get the $1,000 profit out of that? Because in the final analysis, we're saying this is not a good deal. The present value of that $40,000 is only worth $37,000. Because over the span of 8 years, you could have been earning interest on that $39,000. And that interest, geez, I wonder what the interest on $39,000 would be. Let's just find out real quick. 39,000 times e to the 0.016 times 8. Oh my gosh, do you know what the interest on $39,000 over 8 years is? $44,325. Provided I just did that right, which I believe I did. I used the formula A equals PERT. A equals PE to the RT. And I did the principal of 39,000. And I did the interest rate of 0.016 times 8 years. Makes you wonder why we didn't just do that analysis from get-go, you know? How much would my 39,000 be worth 8 years from now? It'd be worth 44,000, which is considerably more than the 40,000 we would have gotten from a continuous income stream. Okay, so I think that helps to make a little sense about why the present value is so much less than what we almost paid for it. Okay, all right, folks. Yeah, and then I'm going to cancel number 10. So thank you, Awesome Center, for letting me know that number 10 is still part of the problem, or still part of the homework. I will delete that. So let me make a little note to myself. Okay. Delete number 10. All right. Well, folks, here we are then. Let's take a moment, because I don't think everyone has come up here. Everybody, you've got 2 minutes. If you haven't come up to choose some problems, come up and choose some problems. And also, if you haven't yet come over here to sign this little form, please come over here and sign it. I still need Carmen, and Nate, you too. You come over, or Nate, you come over and sign this. Well, this is not here. Nick. Oh, wait, Nick, somebody check mark your name for you. Oh, okay. Right, but Mom, did you accidentally sign on Nick's name? Oh, wait, that's Nick. I'm sorry. Oh, Nick. Obviously, because Nick, you're here. Sorry, Nate. Okay, Nate, you're going to sign that up. Daisy already did. Oh, cool, good. So just Nate. Mom, you come over here and sign this. We'll get there, folks. Otherwise, go ahead and choose a couple problems that you'd like to see, folks. I don't know who didn't already choose problems. Did Daisy, did you already choose some? Okay. Thomas, did you already choose some? No. Okay, come on up. Julie, did you already choose some?
Yes.
Okay, great. Rose?
Yeah.
You did. Us, who sent it?
I wrote them down.
Oh yeah, that's right. You wrote them down. Mong, did you already choose some problems? Okay. And then Nate, you're about to. Great.
Oh, you don't have it. What are these? I didn't do very nice. Well, that's great. The flooring. Yeah, the way she was explaining, clicked in my head, like, it was like something. It was like definitely something strange. And I don't know what it is, something changed, and it just didn't work. And so she had to fix her with it to get that. So she was saying everything to you. Yeah. I didn't know. Yeah, but I just went off. Oh, baby. Not tomorrow, Thursday. Every Thursday. Yep, pretty much scheduling it. Yep, every Thursday. So, because I'm like, I'm not gonna come before Wednesday.
John, where's
So where are you? I am up to chapter 13. But she'll that problem that we did in class, the meditation style, concentrating when she was saying next to me. So she went over the whole entire problem. And then and so you do stuff that like her notes are actually you see her notes compared to what we're getting in class.
Okay, Astu, I believe I deleted the question. All right, folks. I'm going to start with doing the problems that you requested. So we'll move along and we'll review the questions that you marked. And if I happen to see one along the way that I think, oh no, we should really clarify this fine and subtle point, then we will do so. Okay, so we're starting with number one. I'm going to go ahead and move this on the board. Pardon me, Thomas. There we go. Fantastic. So, number one. By the way, everyone has a practice test, right? I handed them out last week, but I had quite a few extra copies. So that means that maybe someone didn't get one. Did everybody have one? Okay. So, this is a really interesting problem. Speedometer readings for a vehicle at 13-second intervals are given. So this is how fast the car is going in feet per second. And it says, estimate the distance traveled by the vehicle during the 65-second period, using the velocities at the beginning of the time interval and then the velocities at the end of the time interval. So first of all, what are we fundamentally doing here? If we draw a graph, go ahead and just draw a little graph real quick. We've got our time intervals, which are 0, 13, 26, 39, 52, and 65. So those are our time intervals. And then we have our velocities, which are all somewhere in the 30s or so, 10, 20, 30, no, 10, 20, 30. So our velocities, I'm going to go up to 40, are about 32, 39, 37, 29, 37, and 26. So those are our velocities. Looks like a bit of a jerky ride. And that's your velocity in the car. And they're asking us to figure out the distance traveled. Well, this is the velocity, and this is the time. So how do you calculate distance from velocity and time? What's our fundamental formula? Distance equals rate times time. So that means that if we multiply our velocity times our time, that should give us distance. And in this particular case, if you multiply rate, which is the height, times the time, which is the width, we're calculating an area. And this is how we got into integrals in the first place, is that we're technically calculating the area under this curve. So what they're asking us to do then, instead of actually trying to turn these into triangles and calculate the actual area under the curve, they want us to do a beginning of the time interval, which is a left-hand Riemann sum, and the end of the time interval, which is a right-hand Riemann sum. So how do we do the intervals at the beginning of the time intervals? We use the velocity from the beginning of the time interval. So from 0 to 13 seconds, we're going to say that your velocity was a constant 30. So that's our first rectangle, because we're using that point. And then from 13 to 26, we're going to use the velocity at the beginning of the time interval, and that's our next rectangle that we're going to calculate, the next area we'll calculate. And then from, 26 to 39, we'll use 37. That was our next velocity, so we'll calculate the area of that rectangle. And from 39 to 52, we'll use the value of 29, and we'll do that rectangle. And from 52 to 65, we'll use the velocity at the beginning of that time interval, which is 37. So those are the left-hand Riemann sum rectangles. So how do we then calculate our total area? I'm going to say area equals the distance, which is rate times time, which we're going to do for each and every one of those rectangles. Which is what? Yeah, 32 times 13. So every single width is 13 seconds. So we're just going to go in order from here. So 32 times 13, plus 39 times 13, plus 37 times 13, plus 29 times 13, plus 37 times 13. But that's it. We only use 30. We don't go all the way to 26, because 26 is how fast they were going at the end of the last interval. And we're only using the velocity from the beginning of each interval. And then the fact that all of those are being multiplied by 13, you could factor out the 13 and say that you're really just adding together these speeds right here. So it'd be 13 times 32 plus 39 plus 37 plus 29 plus 37. And that's going to give you an estimate for the total distance traveled using the left hand, or the beginning of the time intervals. Once you do that analysis, the second part of the problem is pretty simple. How do we, I suppose we can finish that one. What do we get?
It is 2262.
What is it?
2,262.
Oh, good. That's what I got to. 2262. That's 2262. What unit? What did we just calculate? We just calculated a distance, so the unit is just feet. It's 2,262 feet. That's how far you just went, because we just calculated a distance. So after doing all that tremendous amount of work to draw a good picture, visualize the left-hand rectangle, and write it all out, how can we quickly write down the answer for doing the end of the time intervals?
26 and take away 32.
Add together these time periods. These are now going to be the right-hand periods. So now the distance equals rate times time would be 13 times adding together these values. And that would be, that's acceptable to me. So long as you're showing some sort of work. This would be the work to show. If you just write down 2,262 feet and that's all you wrote down because you just did it all on your calculator, I wouldn't give you full credit. You need to show me a little work. You need to show that you understand that the area is a representation of the distance, which is really rate times time, and that's why we're chunking these into rectangles. Drawing a little graph like that, you would definitely get full credit. Questions about that? So If we go all the way back, you know, probably a month. Has it been a month since we've been doing integrals? This was one of the first ideas that we did with integrals, is calculating the area of a curvy curve. Okay, next problem. That was number 1. Number 3. Of course, this whole class is being recorded, so you can always go back and look at this work later. Bye, Julie. Do you think I said something to upset? No, I'm kidding. You probably just like Carmen in, didn't you?
Yes.
Hey, it's Carmen. All right. Carmen, if you would, please come up and choose 5 problems that you'd like to see done. All right. Okay, so number 3, approximate the area under this curve from 1 to 3 using a right endpoint approximation. So we're going from 1 to 3. And so already I know that this is the area that I want to approximate. I want to approximate how much area is there between 1 and 3. And how many subdivisions do we want to do? 4. Yeah, Nate?
Oh, no.
Oh, you were holding, okay. So for the subdivisions, what I like to do, folks, when it comes to subdivisions, I take my right endpoint minus my left endpoint and divide by the number of subdivisions. So right minus left divided by the number of subdivisions. That will calculate how far apart the subdivisions are. So I'm doing 3 minus 1 divided by 4 subdivisions. I should have a subdivision every 0.5 units. So I start at 1, and then my next subdivision is going to be at 1.5. And I would draw a line up. And then my next subdivision will be at 2. I'll draw a line up. And my next subdivision will be at 2.5. And I'll draw a line up. And then my next subdivision is at 3. So that's how you calculate how far apart your rectangles should be. The width of our rectangles are 0.5. And how am I going to make my Riemann sum? Are we doing the right endpoint or the left endpoint? Yeah, we're using the right endpoint. So considering each rectangle, you want to make the rectangle as tall as the right endpoint. So you go up, for each rectangle, you go up the right-hand side, and you draw a rectangle. So you go up the right-hand side, and you draw a rectangle. Then you go up the right-hand side, and you draw a rectangle. Up the right-hand side, and you draw a rectangle. That's what makes it a right-hand endpoint. All right. Well, we know how wide each of our rectangles are. They're all 0.5 wide. How tall are they? How tall is this rectangle? 2? How do you know it's too tall? It doesn't look too tall to me, at least according to my drawing. This is 1, 2, 3, 4, 5. It looks like it's 1, 2, and a bit. 2.8? 2 point what?
Right?
There's a formula. It's y equals x squared. So whatever the x value is at the right-hand endpoint, you square that value, and that is the height. Because remember, the function tells you the y-coordinate. So if you want to know the height of each of these rectangles, you square the x input that is where the height is at. So that height on the function is 1. So 1.5 squared is 2.25. And then 2 squared is 4. That's a height of 4. And that one's more obvious. It looks right at 4. And then 2.5 squared is what? 6.25? And then 3 squared is 9. So now we have the height of each of our rectangles. And the problem is pretty much done.
Yeah.
So our total area would be 0.5 times 2.25 for that rectangle, plus 0.5 times 4 for that rectangle, plus 0.5 times 6.25 for that rectangle, plus 0.5 times 9 for that rectangle. And you could rewrite all that as 0.5 times 2.25 plus 4 plus 6.25 plus 9, if you wanted to. Now what did all that work out to be? 10.75? What are the units on that measurement? Doesn't really talk about units, does it? It's just area. So I suppose there isn't really a unit, other than the fact that what we're always measuring is squares. So it's a square units. So if I were to look at my graph and look for one square, well, that doesn't make too much sense. Yeah, there's no units here. Okay. Well, that was it for 1 and 3. Now, we might not do all the problems all the way through to the end. I think if we do all the problems all the way through to the end, we might not finish everything. So as we move along, we might just talk about how to do it. Like, for instance, number 4. We've now done 2 approximation problems. So you're probably now in a good position to do this approximation problem. How would we do it? It says approximate the area under the graph from 1 to 5. So definitely want to start out by drawing in your 1 to 5 markings. Using a left endpoint approximation with 4 subdivisions. Let's practice that subdivision formula again. You do the right endpoint minus the left endpoint divided by the number of subdivisions. Which is what? Yeah, 5 minus 1 divided by 4, which is 4 over 4. So that's nice. So the subdivision is every 1 unit. So starting from 1, you'd have another subdivision at 2, and another one at 3, and another one at 4. And those are your 1, 2, 3, 4 rectangles. And you're going to do a left endpoint approximation. So that means the left-hand side of the rectangle determines the height. So for this rectangle, the left-hand side determines the height. And for this rectangle, the left-hand side determines the height. And for that rectangle, the left-hand side determines the height. This one is all you. Did they give you a formula for that function? No. Do we have any guesses what the function formula is? Yeah, I don't think we have any idea. If you turn your head and look sideways, it could be a parabola, right? It could be a parabola. Or it could be the square root function. You know, maybe the square root function is more appropriate because it should have started out by going pretty quickly. We have no idea. We don't know what the function is. So ultimately, you're just going to eyeball it and say, well, that height looks to be about 1.3. And that height looks to be about 1.7, maybe 1.8. And that height looks to be about 2.3 maybe. And that height looks to be about 2.6. That's totally up to you to estimate that. So to get credit on the test, you would just have to make a convincing argument. You know, actually show me the tick marks, show me the numbers that you're using for your approximations, and then show me the work by doing, you know, area equals maybe width times height, which would be 1 times 1.3 plus 1 times 1.8, and so on. But you're going to come up with your own value. Yeah, Mom?
So I got an 8, but the answer is like kind of different.
Yeah, their answer is weird, isn't it? If
Yeah,
now,
7.99.
yeah. So, Mom, you got the answer of 8?
Yeah.
I got the answer of 8.
Oh.
But yeah, their answer was crazy. And you know what I believe? What do you think? How do you think they got their answer?
I don't know. It's look like somehow dividing.
Yeah, they might have actually known the function and they actually did the real value. No, that doesn't make any sense. I have no idea. I have no idea, Mom, but I like your answer of 8 because I got the answer of 8. Now, by the way, folks, the answer key, you should know that some of these problems I didn't even include in the packet, but the numbers still match up. And for the most part, the numbers match up, so you'll be able to just look and see what the answer is. But a few of the problems I changed it a little bit and I made my own. Like, in fact, on this page where we are right now, if you look at number 6, I made those problems up at the bottom. So the answer key for number 6 is not correct. So, but I'm going to post this online after class, so you can just look at my own to see what the answer is.
Did you get for number 6, 505?
Yeah.
Okay. I just-
Yeah, that's it.
And then I had number 5, which is my final answer.
Oh, you just wanted to check? Okay.
Yeah, I didn't mark it.
Oh, gotcha. All right, so that's it for number 4. Number 5, same thing, but number 5, I want you folks to, if you see this on the test, I want you to actually come up with the function. What is that function? You can all tell me. What is the actual formula for that line? First of all, it's a line, right? So the formula is going to be mx plus b. And we all know the y-intercept, which is 4. And now you just have to calculate the slope, which is down 1, right 4, so negative a fourth. And then you can actually calculate this integral. You can do the integral from 1 to 2 of negative 1/4 x plus 4. So you can actually calculate the integral. It's not a matter of, estimating how much area is underneath that little triangle up at the top. You can literally calculate it, which is pretty cool and powerful. You can do that. I would want you to actually calculate it on the test, yeah. Because it's so much better to get the real answer than just approximate it. What do the instructions say? It says to find the blue shaded area, we would calculate an integral for that function. So yeah, you would need to actually calculate the integral. Okay. And for number 6, did anyone choose number 6? Yeah, a couple people did. For number 6, just notice that I have various limits of integration. So first I want the area from 0 to 5. So just between 0 to 5. What would be a good first thing to do for this problem, folks?
Put in the numbers.
Yeah, put in the numbers. This area is 8. This area, it says area 2 is 3. What does that really mean? And that's negative 3. Area 3 is positive 1. And area 4 is negative 1. Yeah, so you're looking between various different limits of integration to calculate your answer. So for instance, what's the area between 0 and 5?
5.
Yeah, just 5, because you're totaling this up. Okay, let's keep going. Number 6. Wait, that was number 6. Number 7? Oh boy. Now, number 7, can we figure out what the function is? After all, they're just straight lines. But it's a piecewise function, right? So first you'd have this function, and then you'd have that function, and then you'd have that function, and then you'd have that function. So for a problem like this, should we actually calculate the integral of the function, or I think you could just approximate this one. I think the goal here is to approximate it. Now, I feel bad. Here I am saying that for number 7, you should count the squares. And yet, 2 problems ago, and Nate even raised his hand to ask about it, I said, don't count the squares here, I want you to actually calculate the integral. So I suppose I need to be specific on the test then, huh? I would have to say, for number 5, I want you to actually calculate the integral. Because it's possible. This is possible. You can easily calculate the integral. It's just one function. Whereas for number 7, not easy at all. You'd have to have 1, 2, 3, 4 different piecewise functions to calculate all those integrals, and that would take all day. So for number 7, I'm saying you can just count the squares. So you would chunk this up how? You would have this triangle, and then you would have this triangle, and then you would have this triangle, and then you'd have this rectangle. Right? So you're just doing a bunch of triangle formulas, area equals 1/2 base times height. And then you're doing a rectangle formula at the end there, area equals base times height. And you'll calculate all those areas yourself, counting squares, and then you will add them together into these various chunks. What's the area of the first triangle? Well, let's actually do it. It's base times height, so it's 1/2, the base is 2, the height is 1, so that's half of 2, which is 1. So this is really negative 1, right? The area is below the x-axis, so that's negative 1. What's the next triangle? 1/2, how long is the base? 3, and the height is still 1. So that's 1.5, so that's negative 1.5. And what's the area of the next triangle? 1/2, the base is 1, and the height is 2. So that's a positive 1. And the next rectangle, you can actually count the squares, or you can say base times height, 2 times 2 is 4. Okay, and then you'd be able to go about calculating those various integrals. Oh, good. Someone wanted to see number 9. I think number 9 is such a great question. I'm so excited by number 9. I know that in the past we saw a bunch of these questions, and I think we all agreed that those questions were weird. But this is a good question. Here they're giving us which function? The derivative. And the derivative tells us information about the slope. So from the slope information alone, they're asking us what's happening at x equals 1. Is the graph increasing or decreasing, and is it concave up or concave down? So I suppose there's a variety of ways that we can do that. I mean, to find out if it's increasing or decreasing, what do we do? Yeah, we just plug 1 into it to find out the slope. So f prime of 1 would be -4 times 1 plus 5 is 6, and 1 plus 2 is 3. And that gives us, I don't even have to calculate it, the slope is negative. So that means it's decreasing. Of course, I can't help myself to calculate it. 24 times 3 is what, 72? Yeah. -72. So it's definitely decreasing. Now, how could we find out about concavity? Yeah, to do concavity, you could just do the second derivative. The second derivative looks like a bummer here. It looks like we'd have to do the product rule. Should we do the product rule? What else could we do?
Find the 0.9 and 1.9.
Do what?
Find 0.9 and 1.9.
You could always just find the slope of 0.9 and the slope of 1.1, right? Because that would tell you the slope just before 1 and the slope just after 1. That would be one way to find the concavity. And in fact, that's how I did it on my own answer key for you. So I would have then -4 times 5.9 times 2.9. That's pretty simple to type into my calculator. So -4 times 5.9 times 2.9. That gives me -68 point something. And then if I plug in 1.1, that would be -4 times 6.1 times 3.1. And obviously that's giving me a bigger number, 4 times 6.1 times 3.1. That's even steeper. So what does that tell me? Yeah, it appears to be concave down. If I just go ahead and draw a quick graph and I say, okay, here's x equals 1. The value x equals 1 is negative, but at 1.1 and at 0.9, at 1.1, it's even more negative. And at 0.9, it's less negative. And just by kind of looking at that visual idea, what does it appear to be? Concave up or concave down? Yeah, concave down. That's one way of doing it, right? So now we know that it's decreasing concave down. However, going back to, was it Rose who said take the second derivative? Yeah, you could do the second derivative pretty easily, right? You could go ahead and keep the -4 outside, and the derivative of the first times the second, I'm doing the product rule. The derivative of the first, which is just 1, times the second, plus the derivative of the second, which is just 1, times the first, and there's my derivative. So that's -4 times distributing the 1, that's x plus 2 plus x plus 5. So that's -4 times 2x plus 7, which is -8x minus 28. So now if I want to know my concavity, at the value of 1, well, pretty obviously, what is it? Negative. So that's another way of knowing that it's concave down. So you could do the product rule, but let's say you didn't want to do the product rule. How else could you do it? What could you do to this? Yeah, you can just FOIL it, right? -4 times x squared plus 7x plus 10. And then we go ahead and take the derivative. Ooh, we've never done this before, but remember, when you take the derivative, what does the coefficient do? It just comes along for the ride. I can just leave the -4 outside and take the derivative of this, which is 2x plus 7. And do you notice what we got?
Yeah.
Literally the same thing. So we FOIL the inside, and we still get that it's concave down. So that's 3 different ways that you could show your work on that problem. Number 9, we're going to skip number 10. Yeah. Oh, well, 10 and 11 go together, folks. 10 and 11 go together. 10 and 11 are an example of the fundamental theorem of calculus. So maybe just make a note right here. The fundamental theorem of calculus. You notice how I abbreviated the word fundamental? Everybody? Yeah, fun. The fundamental theorem of calculus states what happens if you take the derivative of an integral?
They cancel.
They cancel out. Nate?
I said, do you think we'll have a question like number 9 on the test?
Yeah, I'm definitely going to put one like number 9. Yeah. Yeah, so the fundamental theorem of calculus part 2 states that if you take the derivative of an integral, they cancel out, and you're just left with the function. When we saw this in application, it seems like something real cheap to just memorize. But if here's my function, which is an integral, and I'm going to take the derivative of it, what happens is the integral sign cancels out, but you replace the t variable with x. And in the end, it's just x to the 7th. That seems like something that we just memorize. It's not very exciting. I suppose it's just knowing. The key thing is knowing that the derivative of an integral cancels out. And the answer is x to the 7th, not t to the 7th, right? T was a variable representing how far the integral, well, representing the integral. But the integral, you're calculating the area from 0 to x on the graph. So it becomes x to the 7th. And then at that point, how would you find the derivative at -2? You just plug in -2, right? Now, how about this problem? This is a little more tricky, Nate.
Say it was 3x to the 7th or 3t to the 7th.
Yeah.
Would it still just be 3x to the 7th?
Mm-hmm. This one's a little more exciting, number 11, because they give you the function, but then they want the second derivative. So probably better to find the first derivative first, right? What would the first derivative be? The function with x instead of t. So you'd have x cubed plus 6x squared plus 4. But then to find the second derivative, you go ahead and just do the second derivative. 3x squared plus 12x. What, Rose? Oh, yeah, yeah. Yeah, so not bad at all, those problems. They're not computation heavy. It's just an awareness that the derivative and the integral cancel each other out.
So it becomes x instead of t.
It becomes what?
It becomes x instead of
T. Yeah, t becomes x. Yeah, x instead of a t, exactly right. Okay, well, it looks like we're going to skip over 12, 13, 14, 15. And that's just fine. I mean, 12 is just calculating an integral. 13 is just calculating an integral. 14 is just an integral. It wouldn't hurt just to look at this one, 3 over x. What do you do with the 3? You can just bring the 3 out front, right? And what is the integral of 1 over x? Yeah, natural log. So that one's just something you purely memorize. Now, technically, it's the natural log of the absolute value of x. And any integral on the whole test that you do that's not a definite integral. Because what's the answer going to be from a definite integral? When you do a definite integral, you're actually calculating an area. So the final answer is just going to be a number, right? It's just going to be a number like 300 square feet, right? So anytime you do a definite integral with upper and lower limits of integration, you're going to end up with a number. Whereas when you do an integral that's an indefinite integral without an upper and lower limit of integration, the answer is going to be a formula, right? So whenever the answer is a formula, I know that we haven't spent a lot of time focusing on this, but what's the end of every formula from an integral? Yeah, plus c. Because theoretically, there could be a constant value there, which then when you take the derivative of that formula, the derivative of a constant is 0, and you would get back to this formula over here. So if you're doing a definite integral, the answer should always be a number. If you're doing an indefinite integral, the answer should be a formula plus c. When I took calculus the first time, like you folks, my teacher, whenever she didn't see the plus c, she would write a big boo on our test. It all really got to us psychologically. We didn't want to be attacked by the boo. We all joked that she had a bat that she carried around late at night, and it had the word boo on it. And none of us want to get hit by the boo bat. Anyway, that's my childhood. All right, let's keep going. The 15, same thing, you're just doing an integral plus c. 16, the value of that definite integral. What should the answer of a definite integral be? Yeah, a number, some sort of a number. We're actually calculating an area here. So how do we calculate that integral, folks? We're going from 3 to 6 of 1 over x squared. You want to find the antiderivative. What is the antiderivative of 1 over x squared? You have to rewrite 1 over x squared first. Yeah, move x to the numerator as x to the negative 2. Exactly right. Now you can do the anti-power rule. So that's important. Of quite a few of these problems, you have to rewrite it as a normal power function. So instead of 1 over x squared, it'd be x to the negative 2. And then you just do the power rule, the anti-power rule. Right, and that's fine. The anti-power rule means you add 1, so x to the negative 1, divide by the resulting number, negative 1, and integrate from 3 to 6. Yeah. And at that point, I would actually rewrite this to make it look nice. I would write this as 1 divided by negative 1 is negative 1 all over x. So I would have negative 1 over x integrated from 3 to 6. Now something like this, I suppose you could type it into your calculator, but it would look a lot nicer since it's so simple. If you just go ahead and do negative 1 over 6 minus negative 1 over 3. So this is easy enough that you can just go ahead and calculate. You've got a double negative, which is plus, and a negative of 6 plus a third. You have to find a common denominator. So I'm going to multiply times 2. That gives us a negative of 6 plus 2/6, which is 1/6. I suppose that's as good a time as any to take a break. We finished one column, that's nice. And then we'll come back and do the rest. So folks, the time is 11:01. Let's come back at 11:11. If you haven't done so already, well, I'll just call out the people who I need. No one. Wow, thank you, folks. Everybody's done. That's great. Oh my goodness, this is good to know. So a lot of you need the class mat213, but you're not enrolled yet. What's that?
Part of the.
Oh, gotcha. Oh, you're not sure. Okay, well that's fair. That's fair.
No, I'm not. Part of the. I was enrolled.
Yeah.
You were enrolled,
Yes, but
but then you unenrolled?
No, I was enrolled and I go to rate my professor.
Uh-huh.
Said the professor is so hard, blah 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 blah. So it's just dropped it.
Oh, so you just dropped it.
Yeah.
But do you need the class?
Yeah,
You do need it. Oh, so you're gonna re-enroll?
maybe.
Okay.
Then even next semester, wait until a good professor.
Oh, you're saying you don't want to take it from that professor. Have you had that professor before?
No,
How do you know?
I just go to rate my professor.
Mm. And do you believe Rate My Professor?
Probably.
Probably.
Mm-hmm.
Do any of you guys go to Rate My Professor?
My daughter did.
Yeah.
I got a class with it.
I've never gone. I've never looked.
I
Because
did for the science.
you did for the science?
I did for your class.
Oh, you did?
No.
Oh, that's true because you didn't know me. I've never looked at Rate My Professor because I don't trust people. I think sometimes people have a really negative attitude of someone, and that says more about them than the professor. But then again, if everybody says something negative, then maybe that's true. I don't know. I'm torn. Have you looked at Rate My Professor? No? What kind?
Not for you, it's for the professor who teaching math to 18. Well, the majority of people say his class are so bad, he did not win every question.
Oh, so you're saying the vast majority of people
Yes.
were in agreement.
So I
Okay.
just drop it.
I gotcha. Yeah, that's a tough one. When I taught high school, some of the teachers thought they were being helpful when they said, oh, I had little Billy in my class last year, and you have Billy in your class next year. And I just need to tell you, little Billy is a terrible student. I would actually have teachers come up to me and tell me that, like, oh, JW, you've never had Billy before. He's awful. And then you know what would happen? I would get Billy in my class, and you know what? He was great. Great student. Fantastic student. No problem at all, did all of his work. And it just leaves me wondering, is it the student or is it the teacher? What do you think? In the case of little Billy.
I think it's depend on
Yeah.
like sometimes teacher they give the rule and they never follow it. Student when they broke the rule, the teacher didn't respond or like give
Consequences.
Well, I
consequences.
think
But sometimes it's broke, they're gonna take serious.
Yeah, exactly. Yeah.
I think that people tend to forget that they have lives too outside. And so like they can be really good one semester and then the next semester it's like, what the hell happened?
Sure, they could be better.
And then the following semester or whenever they can get better. I mean, I've run into that.
Mm-hmm. Yeah, students can change, teachers can change.
Mhm.
Okay, so but Carmen, so you're gonna take the class some other time, eh?
Yeah.
Oh, but not next semester.
No.
Okay.
My phone is getting old.
You're what?
My phone is getting old.
Oh, isn't it nice that you can just charge your phone?
And I should put a hairband around it.
Oh, there's a rubber band around it. Oh my
That's the
gosh.
only way you can charge it. And that's why the reason I did not hear the alarm this morning.
Ah, gotcha. Well, that's pretty. That's a bummer. Well,
Why you are not teaching till 18 minutes?
I don't know. It looks like a fun class. I would actually really like to, but I think it's because they already have a teacher who does it.
There's just only one.
Yeah, just one. I'm going to ask because I'm going to start teaching night classes. Next semester, I'll teach one night class. So that looks like a fun class to teach. Nate,
I just had a quick question. For number 5, you know if the answer key's wrong? Or,
well, let me look. The answer key could be different because I did edit some of the problems.
we got -1/4.
Yeah, that's correct for the function. What does the answer key say?
Just x was 4.
Really?
Yeah. Oh, no, it just said negative. Oh, because then the answer is -1,252. So I thought it was 2 separate.
Oh, yeah. No, yeah. The answer key is saying -1/4 x plus 4.
Because the area came out to -1,252.
I got the area of 3.625.
Really?
Well, I mean, just look at the graph. It's definitely a positive area.
No, yeah, that's what I used to touch it.
Oh, are you using your calculator to do it?
Yeah, that's.
How do you do that? I mean, you're allowed to. There's nothing wrong with it. I'm just curious. Are you using the graph?
Oh, no, I did. I typed it in. Well, I did it wrong.
Oh,
I typed
well,
it in.
yeah, let's see how you do it.
No, I just did it. Typed the function.
Really? Yeah, I'm not sure because I'm.
We used the other one to show, but that's not for integrals.
Oh, well, I don't think I showed you that method. What I have done is I'll
It's
do
literally in the first
5x plus 4, and then from there, well, let's choose that.
That's easy to find.
From there, I do the integral, and then I can type in
Because it has
to
titles.
1 to 2. So lower the way I type 1, lower the way I
Yeah.
type 2, and then it does it. So that's. But you were doing something different. You were gonna do. Gosh, how does it?
I did that in one
How do we
sitting while I
do
was
that?
sitting talking.
Is it under math? And then you're gonna do the integral of your variable? Is that what you're doing?
No.
Of x from.
Because
No,
there's
that
one
can't be
part
right.
just wasn't clicking
This one.
for me,
No,
so she
yeah.
did like the
Oh, so
circle
what were you
bubble
doing?
thing,
I
and
just
she
had-
read it out.
I-
and then-
Oh, okay, you did it the way I did it. Oh,
Yeah,
okay.
Yep.
Oh, what?
This thing.
Oh, you guys must have done it the same way. You also got it.
I got this hard show too. It's working together.
But you did it on your calculator?
Well,
I'm trying to get it to actually show some work. Yeah, show some work so I can see how you did it.
And she used to like whiteboard or something. Consolidation, which is interest limit. And then which is were trying to journalize it, and so she showed me that. And then 20, and then it was 40%. So it's interesting. Yeah, the self-confidence. Just the way,
Okay, so I just did it by hand here, maybe it went too far again.
Oh, strange. Oh, well, this is definitely important then. Let's see what happened. Oh, I don't believe you did the integral yet. That's what it is. You haven't done the antiderivative.
Okay.
You gotta do the anti-power rule, and then you plug it in. Carmen, I bet that's what you did as well then. You must have just plugged in the numbers as is.
Thank you.
Oh yeah, you're welcome. Well, everybody's back. It's not 11:11 yet, but let's go ahead and get started. We are now moving on to number 17. Oh, great. Number 17 is a great problem. Number 17 pulls together a whole bunch of different anti-power, well, derivative rules. There we go. So number 17. Each of these is a different rule. Isn't it wonderful? It's wonderful. So let's write them all down separately. We have 3x to the fourth is just 3x to the fourth. How do we need to rewrite 6 over x? We could rewrite it as 6x to the negative 1. Well, that's true too. We could pull out the 6, only if we break it up into lots of different integrals. I actually asked that in a trick question kind of way. We're not going to rewrite it at all, because what's the integral of something over x? Yeah, the natural log. So this one we'll actually just leave right as it is, because, I mean, we could write it a little bit. Mung, I forget, did you say rewrite it as 6 and 1 over x? You could do that, because with 1 over x, the antiderivative is just the natural logarithm. Okay, but then how would we have to rewrite 3 over x to the 6th? Yeah, this one we definitely want to do the negative power. So Mung, you're absolutely right. This one you'd want to rewrite it as x to the negative 6th, whereas this one we don't need to rewrite it as x to the negative 1 because we're not going to do the anti-power rule. Okay, and then what about 5 root x? Yeah, 5x to 1. Okay, so we did lots of rewriting, a normal power function, a natural logarithm, a negative, and a fractional. So now we go ahead and take the antiderivative of all of them. So what's the antiderivative of 3x to the fourth? Yeah, there we go. 3 over 5x to 5. And then the antiderivative of 1 over x is just the natural logarithm. And remember to put the x in absolute value. Adding 1 to 1/2 is 3 halves, and then dividing by 3 halves. So I really recommend that you do that fraction work second. Just write it down. Just do the rule. You add 1 and then divide by the resulting number, add 1, divide by the resulting number, and then go back and do one more step where you actually clean everything up and make it look nice. So 3/5 x to the 5th plus 6 natural log of x plus 3/5. Oh, no, actually, how do we clean this one up? It's a double negative, so it's plus, but how do I write down the final answer? Where does the x to the negative 5 go? In the denominator. Yeah, 3 over 5x to the 5th. And then how about this last one? 5 divided by 3 halves is really 5 times 2/3. So if you want to show a little work somewhere, 5 times 2/3 is 10/3. So we have 10/3. And honestly, the x to the 3 halves can just stay. I believe the answer key has it as x to the 3 halves. Come on. Oh, this part? 5 divided by 3 halves. So 5 divided by 3 halves is really 5 times the reciprocal. And so I multiply that out and I just get 10/3. So that's the 10/3. And I think that's it. I believe that's what the back of the packet says. So really good problem because it draws on so many different rules. Okay, number 18 we're going to skip, and that's fine, because what's the antiderivative of 1 over x? You pull the 5 out. And the antiderivative is? Yeah, natural log. So it'd be 5 times the natural log of x integrated from 1 to e to the 4th. So I won't finish that problem, just going to suggest it. Okay. Number 19. Number 19. Someone did request to see it. Number 19, how would we do it?
So 3 over 8x.
Yeah, 3 over 8 x to the 8th plus
X to the 6.
6 over 6 x to the 6, which you then can clean up. And you're going to integrate that from -3 to 4. And something like this, as a calculator tip, this is 3/8 x to the 8th plus x to the 6th. And we're integrating from -3 to the 4th. As a calculator tip, whether you'd like to try this or not is up to you. I go to my y equals, and I graph that function. Now that might sound crazy at first. Why are you graphing the function? 3/8 x to the 8th plus x to the 6th. So I go ahead and graph it, and I have my function there. Because then what I do is I use my trace, actually not trace, but above it, second calc, right above that, and I can type in any value I want. So now I type in the value of 4, and that tells me immediately that the answer is 28672 minus, and then again I go second trace, and I do a value of -3, and oh, your window has to be appropriate. So then I plug in a value of -3, and it just tells me those values right away, 3189.375. And that way I only have to type the formula in once, and I'm using my graphing calculator to actually get those values. Of course, now I have to actually subtract them. 28672 minus 3189. Does anyone have a better way of doing that? I suppose there is another way you could do it. Once you have it in your graphing calculator, you can also go to the table function. So if you go second graph and go up to the table, it will immediately tell me the values of 4 and -3, because I can just look in my table. So that just cuts down a little bit on the computation. Yeah, 4 was 28672 and -3, yep. So all those values are in your graphing calculator if you graph the function. It's a little bit easier than actually typing it in. Of course, what else could you do, folks? You could just type into your normal graphing calculator screen 3 divided by 8 times 4 to the power of 8 plus 4 to the power of 6. And then you can hit second, enter, call back up the same thing, and just go back and replace the 4s with -3s. So I suppose there's a lot of different ways that you can do this on your calculator. Okay, well, that's it. That's number 19. How about number 20? 2 people would like to see 20. Ooh, a very nice integral indeed. How do we do number 20? How do we do number 20? Any thoughts?
No.
Separate it how?
X, 8x squared over root of x plus 9 root of x.
Yeah, you do 8x squared over root x, and then plus 9 over root x. That's a good start. Then what do you do?
Move the x, root x to the numerator.
Yeah. So then we would have, that's really, I'm going to do one more step. Ax squared over x to the 1/2 plus 9 over x to the 1/2. Am I writing my dx's? There we go. And then what? Then you just move that x to the 1/2 up to the numerator. Or what you're really doing is, well, in this case, you're subtracting 2 minus 1/2. So by moving the x to the 1/2 up to the numerator, it's x to the -1/2. So now we have the integral from 4 to 5 of 8x to the 3/2 plus 9x to the negative 1/2. Did I do that correctly? What is 2 minus 1/2? Yeah, 3/2. Because I could read, instead of 2 minus 1/2, I could say 4/2 minus 1/2, and that is for sure 3/2. So now we're doing that integral. It's a lot of clever manipulation, right? Because now at this point, you can just do the integral by doing the anti-power rule. So if I'm going to add 1, that's like adding 2/2. So that would give me 8 divided by 5/2, x to the 5/2. And then if I add 1, that gives me 1/2, so that's 9 divided by 1/2. Did I do that right? I added 1 to the exponent and divided by the resulting exponent. And then you can clean that up a little bit. Mong, how do I do 8 divided by 5/2? 8 divided by 5/2 is really what?
8 times 2.
Yeah, exactly. So then that becomes 16/5. And if you do that in your calculator, you could just get the answer of 5.2. Nothing wrong with that. So then you have 5.2 x to the 5/2. And then what's 9 divided by 1/2? 9 divided by 1/2 is the same as 9 times 2 over 1, which is just 18. So now we have 18 x to the 1/2, evaluated from 4 to 5. When you multiply two variables, you add the exponents. Yep. Okay, what was your final answer? Well, so again, at this point, you have your calculator work to do. Now the rest of the problem is on your calculator. You take that formula, plug in 5, get a number. Take that formula, plug in 4, get a number. If we want to compare, I got 219.13466 minus 138.4, which gave me a total of 80.73. That last part really is up to you folks on your calculator. You know, I expect that all of your work up till then looks like that. But then there's going to be magic where you plug it into your calculator and get the numbers and get your final value. Okay, well, that was number 20. No one asked for number 21. That's fine. 22. Oh, good. Folks, when we did this problem in class, we had a question about it, but class ended and then we left. I don't know if you remember what our question was. Well, let's just go and start the problem. The company's marginal cost function is this. Remember, the derivative of cost is marginal cost, which tells you what? Marginal cost tells you the cost of, like, let's say I wrote C prime of 5. What is that calculating the cost of? The 5th item, not 5 items. If I wanted the cost of all 5 items, I'd write that. That's the cost of all 5 items. If I just want the cost of the 5th item, I take the derivative of C and I plug in 5. So this is the cost of 5 items, whereas this is the cost of the 5th item, right? So that's just notation of what it means. So in this particular problem, we're saying the company's marginal cost function is given, X is the number of units, find the total cost of the first 36 units. So if you wanted the cost of the first 36 units, theoretically, you could write down C prime of the first unit plus C prime of the second unit plus ... all the way up to the cost of the 36th unit. Would that be fair? Is that the cost of the 36 items? That would be the cost of the first item, the cost of the second item, all the way up to the cost of the 36th item. That would be the cost of all 36 items, right? Find the total cost of the first 36 units. So doing the integral then, doing the integral of that cost function, this was the question we had, you would think that you would go from 1 to 36. Well, what are they asking us to do?
0 and 36.
Yeah, 0 to 36. So why is that? We didn't answer this question as we all left class that day. Hmm?
It's easier.
Oh, maybe, so it's easier? There's a real good reason for it.
Because like you can start with nothing. You start with nothing.
Yeah, somehow you start, what does it mean that you're selling the cost of no units at all? Is there a cost associated with not making anything? Believe it or not, there is. What if the cost function was 3x plus 1,000? Right? So 3x represents your variable cost. It costs $3 to make each unit. But 1,000 was your fixed cost. Right? So this was your upfront fixed cost, and this was your variable cost. And what is c prime of x? The derivative would just be 3. And that says that you're charging $3. The cost is $3 per item. And if I did, if it was really $3 per item right here, I would just have 3 plus 3 plus 3 all the way up to 36. Where would the $1,000 be? There's got to be a fixed cost in there somewhere. If I'm calculating the cost of the first 36 units, it better include the 1,000 in fixed costs. So how do you get the 1,000? That's the fixed cost. The fixed cost is the cost of selling the 0th item, because that's going to theoretically capture that fixed cost that was up there in the beginning. I hope that makes sense, because that's what we figured out after class. All right, so that's why we're going all the way from 0, because from 0 to 36 is going to capture the fixed cost, which the marginal cost does not capture, because that's only looking at the $3 per item. Okay, so how do we actually do it? From 0 to 36 of 17 over root x, what do you do? Do what? Yeah, you're going to do the antiderivative. What literally should we do? Yeah, we could have 17x to the negative 1/2. If we wanted to, what could we do with the 17?
Outside.
You could bring it outside. Maybe there's no real point in that, because when we do the antiderivative, we're going to add 1 to the exponent, so negative 1/2 plus 1 is 1/2, and then we're going to do 17 divided by the 1/2, and then we're going to integrate from 0 to 36. And 17 divided by 1/2 is? Yeah, 34. Because 17 divided by 1/2 is 17 times 2, which is 34. So now we have 34. X to the 1/2, what's that? The square root of x, integrated from 0 to 36. Wow, that's actually a remarkably clean integral, isn't it? 34 root x.
And that doesn't have to go back and move the space next to it.
Correct, because it's positive now.
Okay.
Yep, so that means we're going to do 34 times root 36 minus 34 times root 0. So that's 34 times 6, which is what? Is it 204?
Yes.
Okay. That's a really good problem because it demonstrates a deeper conceptual understanding of what this marginal cost function is, and the fact that, you know, the marginal cost of 1 and the marginal cost of the second item all the way to the marginal cost of the 36th item, you still need to include the marginal cost of the 0th item, which captures the fixed cost. All right. Well, what was that, 22? So 23, okay, good. We're about to start reviewing U substitution. It's been a while since we've done U substitution, and since we've done integration by parts, which is even more sophisticated, perhaps we've how to do U substitution. So here's an integral of x squared times x cubed minus 10 to the 36th. How does U substitution work? Well, fortunately, they're telling us. They're telling us what U substitution to do. And they're saying, let U equal x cubed minus 10. So there will be one problem in which I tell you what U to use, but on the other problems, you'll have to know what U to use. So why did they say to let u equal x cubed minus 10? What's du? Yeah, the derivative, which is 3x squared dx. And what do you do with the 3? Bring it back over here, so it's 1/3 du equals x squared dx. And now we can understand why we use that u. Because the u is going to take care of the x cubed minus 10. And then the du is going to account for the x squared and the dx. Remember, we need to choose a u value that will completely replace the entire integral with a different integral. And we chose, and what you'll always notice is that whatever your u is, you better be able to find the derivative of u just outside, where we did. The derivative of x cubed is 3x squared, and there was an x squared there. So now we can go ahead and replace everything. We're actually now doing the integral of x cubed minus 10 is u, so that's u to the 36th. And we're replacing x squared dx with 1/3 du. Isn't that fun? Isn't that just so much more satisfying now? Because in the beginning, it probably was confusing, a little mysterious. But wow, that really simplified that integral tremendously. And then if you wanted to, you could even bring the 1/3 outside to make it look even better. Wow. What's the integral of u to the 36th? Yeah, add 1 and divide by the resulting number. And we still have the 1/3 out front. And we're not integrating a definite integral. So that's it. It'd be 1 over 111 u to the 37th. And then what's the last thing you do? Yep, plug back in your u value. So that's really 111th x cubed minus 10 to the 37th. Did I already make a joke about how we could start doing u substitution in our own lives? I think that'd be interesting. Like you're about to talk with a boring coworker. You're like, I'm going to do u substitution. Or maybe you're about to do a chore at home that you don't like to do, and you're like, u substitution. I don't know what that means exactly. You know, I'm just brainstorming. How can we do u substitution in our own lives to make something complex into something easier? I don't know. Okay. Any questions about that one? Doing u substitution? Maybe we won't do all the u substitution problems because that's the gist of it. Maybe we'll just choose the u value, and then you can proceed to do the u substitution yourself. So number 24, did someone ask for number 24? Yeah. What's the u? So let u equals what? Now remember, the main idea is whatever you choose for u, you better be able to find the derivative of u also within the integral. So what should our u value be? And you know what, folks? It might be helpful if we clean this up a little bit. Let's bring the 2 outside. All right, let's make this look better. Bring the 2 outside. That leaves us with 1 over x times natural log of 9x. And the dx is at the end.
I think u is always natural.
What?
U is always natural.
Oh, yes. Typically, when there's a natural log, that's a good choice for you. Yeah.
So you can just put omega in x.
It's going to be u is the natural log of 9x. Is that what you're saying, Mom?
Yeah.
Yeah. Mom, you're always a natural log. No, I'm kidding. Okay.
Oh, you remember that.
Yeah. So, yeah, that's a fine choice. If u is natural log of 9x, then what's du? This is actually the chain rule, because you do the derivative of the outside. So the derivative of natural log is 1 over the argument. So 1 over the argument times the derivative of the inside function. What's the derivative of 9x? 9. And what happens to the 9's? They cancel. So really, du is equal to 1 over x dx. Plus what? And that worked out great, because now we have, in fact, accounted for everything in our integral. We have the natural log of 9x down there in the bottom. We have the 1 over x, and we have the dx, so it's all there. I'll go one more step with you, and then you finish it yourself. How do we rewrite all of this? It's 2 the integral of
1 over u.
Correct. 1 over u du. Because the 1 in the numerator is there, because we have to have the 1 over x. And then the natural log is in the denominator, so the u has to go in the denominator. And the 1 over x and the dx is accounted for by the du itself. And so it's simply 1 over u du. And then you take the integral, and then you switch back to your original variable at the end. Isn't u substitution fun? Yeah, that's great. Nate?
What would be the integral of 1 over u?
What's the integral of 1 over u?
Yeah.
You tell us.
Um,
The integral of 1 over u? That's simply one that's memorized. You know it.
no.
Yeah, natural log.
Okay.
Yep, it's just the natural log of the absolute value of x. So it'll be the natural log of, yeah. Okay. Let's keep going. I know I'm not finishing the whole problem with you, but you can finish the problem. And this gives us more time to keep going. The next two problems are both u substitution. And so I'll just help you find a value of u. Did any of you want to see the end of that problem? Or are you okay to go? As I said, I posted the answer key online, so you can always go back and see it there. What would be your choice for u here?
11 plus
Yeah, that seems like a pretty natural choice that, I think for the most part, we all have a gut feeling that you go for the inside function. Or as Mong said, if there's a natural log, make that your u choice. So our choice for u is either the inside function or the natural log. And if that's the case, then our du is simply 6x to the 5th, and you bring the 1/6 over. The 1/6 du is equal to x to the 5th dx. And that seems pretty reasonable. So what will your substitution give you?
Because you have x to the 5th is u. X 1/6.
Yeah, 1/6 square root of u du. And is that clear? You have the x to the 5th and the dx in the front and at the end. So that's why I replaced, I put 1/6 in du to replace x to the 5th and dx. And then otherwise we just have the square root of u. And you could bring out the 1/6 if you like. Not that it really matters. And then you'd have the integral of x to the 1/2. You do the anti-power rule. So you add 1, so that's you do the 3/2. Now, the fact that I already have the 1/6 out here, how do you divide 1/6 by 3/2? Should we write that like this? 1/6 divided by 3/2? I mean, you can, right? Because that is, in fact, what we're doing. We're dividing the 1/6 coefficient by 3/2. You could write it that way. In fact, I don't know how else you would write it, unless you wrote it like this. You could do 1/6, 1 divided by 3/2. Maybe that's not as desirable either. Or what could you do? Could you just go ahead and write 1/6 and multiply by the reciprocal? Maybe that's the best looking one so far. Is instead of dividing by 3/2, you just go ahead and say to yourself, I'm multiplying by the reciprocal. That's probably the best. And then the 2 goes into 6 3 times, and what do we have? 1/9 u to the 3/2? Is that what everyone got? Yeah. And then you back substitute, and we're done. So 1/9, 11 plus x to the 6th, 1/9, how about? To the power of 3/2. Have any of you ever done math on an airplane? You get on an airplane, you got 5 hours on your hands, and just start doing some math? Woo, boy, it makes that plane ride go by, folks. You might consider it next time. Just bring your calculus book with you and do some of the problems at the end of the chapters we haven't done before. You might really like it. Okay, what u substitution will we do next? Yeah, probably t plus 5. That seems like a pretty good choice. U is t plus 5. And du is simply 1 dt, which is really just dt. And again, you could pull the 2 out front if you wanted. So you had 2 outside the integral of u to the 7. Is that correct? Oops, not dt, du. Okay, I'm gonna leave that one for you guys to do. Because with just a little bit of time left, I wanna move us along. Oh, and plus 26 wasn't even one that we asked to do. All right, moving along, let's do number 28.
May I have a quick question?
Yeah, what's your quick question?
Where is 2 over 3 comes from? No, for 24.
Because you add 1 to 1/2, so 1/2 plus 1 is 3/2, and you divide by the resulting exponent. So if you divide by 3/2, that's multiplying by 2/3.
Oh, okay. Never mind.
Okay.
Thank you.
Sure. Okay, what's our next one? 28. Find the integral of 400 e to the point 11x. We reviewed this at the start of class. How do you take the antiderivative of e to the nx? The integral of e to the nx is? Yeah, 1 over n e to the nx. So you simply divide by the number that's up there. So pretty simple, 400 over 0.11 e to the 0.11x. And it's not a definite integral, so we're not calculating an area, we're just done. Although, what should I write? Plus a constant. I know that I was very inconsistent with you folks about making us write down plus c. Because, you know, that's the bulk of the answer, and just writing down plus c is just something you do for form. Okay. Did anyone want 29? No, let's move on to 31. Okay, good. Integration by parts. We definitely did want to review some integration by parts. So here we have 8r e to the r dr. And folks, for the test, I really hope that you will write down your box like we were doing in class. So you have your choice of u, your choice of v. You're going to choose u, and you're going to choose dv from the problem. And what was guiding our choice? You choose u such that when you take the derivative, what happens? Yeah, it becomes simpler. And you choose your dv such that when you antiderivative, yeah, it's just not worse, or at least not considerably worse. And my downward arrow implies that we're taking the derivative, and my upward arrow implies we're taking the antiderivative. So what will our choice be for u and dv? What will get considerably simpler, 8r or e to the r?
8r.
Yeah, 8r would be a good choice. So if u is 8r, du is simply 8 dr. We have to remember to write dr. And so our choice of dv was e to the r dr. And so the antiderivative is just e to the r, because the antiderivative of e to the r is e to the r. Okay, that's part of the work. Now we have to remember what the formula was. Who remembers what the formula was? Yeah, the integral of u dv, which is what we start with, is uv minus, yeah, v du. We switch those. So we're starting with our choice of u and dv, and it equals u times v minus the opposite, which is v du. So I'm going to write it down just to check that I got it right. If my choice of u is 8r and my choice of dv is e to the r dr, okay, good. That's still my original problem. And then uv is 8r e to the r minus the integral. So now v is e to the r, and du is 8 dr. So I have to slip an 8 in there and write dr. Did this integration by parts work? It did work. How do we know it worked? What are we looking at right now to say, oh, good, it worked? The what? this integral is easier than the original integral. That's how we know it worked. Integration by parts works if you end up with an integral that's easy to do. And this is indeed easy to do. It's just 8 e to the r, no problem. We can bring the 8 outside, leaving behind just the integral of e to the r, which we all know. The integral of e to the r is just e to the r. So we have 8 r e to the r minus 8 e to the r. Are we done? Yeah, we are done. So that was integration by parts. You'll have at least a couple U substitution problems on the test and at least a couple integration by parts problems on the test. We should do one integration by parts with a definite integral, because you'll notice here it was an indefinite integral. It's just a formula. But let's do one before we leave right now. Let's just see. Did someone choose it? 32. That's 32 is just like 31, right? It's just a variable in front of e to the. The problems are virtually identical. So we'll skip 32 and do 33. Ah, good. Let's do 33, because that's an actual definite integral, and we're actually calculating an area. And that'll be all we have time for this afternoon. So we're going to end by doing 33. And then my question for you, because I love all of you, is would you like me to make a video of solutions for 34, 35, and the ones you chose? Or is it enough that I just post the answer key?
I think the answer.
I mean, the answer key probably will be enough, because then you can just look at my work and see, and you can email me as well. But if any of you, okay, if any of you have more questions that you want to ask before the day of the test, please email me. And I will give you a full description via email, or you can even call my office. We could talk it out over the phone, or you could come to my office hours. Because I feel bad that we're not finishing all the problems. What are we doing, 33? We still had 1, 2, 3, 4, 5, 6, 7, 8, 9 problems that people wanted to see. I want to give you all the support you need.
Then how about move the test next week?
What's that?
Then how about move the test next week?
You know, I could do that, Carmen, but that would take away one of our days of final exam review. Do you want that?
How about just take away the final exam?
Ah, just take away the final. Okay, no. All right, let's do this problem, folks, before we leave. What is our choice for U? Let's draw our box. We want a U and a V. We want our U to become simpler and our dV to become not worse. Now, of course, Mom already gave us an idea. Mom said that anytime there's a natural log, make that U. You're the natural log. That's a pretty funny joke. I'm going to like that one. So let's go ahead and just try the suggestion. U is natural log of T. Folks, does that seem reasonable? Yeah, I like the idea. The book even said so. If you read the textbook, which I'm sure you all did, the book even said that when there's a natural log, let that be U. So then du is 1 over t dt. And so dv would be everything else. That was our natural log. So dv must be 6t squared dt, right? Everything else is our dv. And so what's the antiderivative of 6t squared? Yeah, we add 1 to the exponent and then divide by the resulting exponent, and 6 divided by 3 is just 2. So that's 2t cubed. Is that what everybody got? Yeah. All right. Well, I would write down the formula first. The formula is u dv equals uv minus v du. Just checking that we did the right thing. U is the natural log of t, and dv is 6t squared dt. Yep, that was the original formula. So uv is the natural log of t times 2t cubed. And now we have the integral of v, which is 2t cubed, times du, which is 1 over t dt. That's really exciting. That was a neat, exciting thing that happened there. What happened? Because we're doing t cubed times 1 over t, one of the t's cancels out. So for sure, the integral that we left with was easier than the original integral. So I'm going to rewrite this portion as 2t cubed natural log of t minus the integral of 2t squared dt. Now, here's the key part. We're actually doing a definite integral from 1 to e. So I'm going to move my work up here so we can all see it a little better. When we have 2t cubed, natural log of t, minus the integral of 2t squared dt, I realize that we're doing the integral from 1 to e on this one, but we're evaluating the whole thing from 1 to e. Because this little portion still needs to be evaluated as well, right? Because we're doing a definite integral, the answer should be a number. The answer should be an area, not a formula. Yes, Clarissa.
What is the second 2t squared?
Because it was 2t cubed over t, and one of those t's canceled.
Okay.
So it was just 2t squared. Okay, so what's the integral of 2t squared? We add 1 to the exponent is 2t cubed, and divide by 3, so that's 2/3. So that is what we're evaluating from 1 to e. The whole thing. Even though this portion was outside of an integral symbol, it still gets evaluated from 1 to e. Did everyone get that integral? Okay. So this you might want to just plug into your calculator, right? You might want to plug this whole thing in your calculator so that it will easily evaluate plugging in e and then subtracting, plugging in 1. After all, what is the final answer for 32? It's just a number. So you can look up the answer key. 32. Wait, this is, oh no, not 32, 33. Yeah, 27.447. Yeah. So you have to plug all that into your calculator to get an answer. Now, folks, let's say that you're doing this problem for the test, and you nail the UV box, and you nail the integral, and you nail the actual final integral, and then you get a different decimal. How much credit am I going to give you?
All of it.
A vast, vast chunk of it. Yeah, I'll give you so much of it, it's true. I'd probably only take off 1/2 of a point if you did everything right and then you just typed it into your calculator wrong, right? That's such a minor thing. It's a calculator error. So you're right, Rose. I'll give you most of the credit. Okay, folks, I'm going to go ahead and write down that we got through 33. So I'll do 34, 35, and 38 through 44. For anybody who wants it, if you email me, I will help you through those problems. Otherwise, I'm posting the answer key right now. And I'll see. Oh, yeah. And I'll also open up Math AS so that folks can go back and work on old assignments.